Our next speaker is Professor Joe Lyons. I don't think he needs much introduction to our vector community, a very well-known personality. Joe was originally trained as a population geneticist, and Prof. Joe Lyons studied medical parasitology at the London School of Hygiene and Tropical Medicine. Since 1983, he has worked on practical methods for malaria vector control. For the first 8 years of his career, he lived and worked in Tanzania, largely in field research on bed nets and their effects on mosquitoes. He's also worked as a consultant, often to design and or evaluate projects and programs, and more recently working with donors and international agencies in higher level strategy and policy development activities. Professor Lyons has worked in about 20 different countries, mostly in Africa and Southeast Asia, but also a little in Latin America and China. Joe's interests include the links between basic biology and public health, and the multisectoral nature of malaria, the influence of landscape, land use, housing and development, and what residents can do for themselves to reduce the risk of malaria while they are waiting for the government to deliver the promised interventions. So I, for one, am really looking forward to this presentation by Professor Joe Lyons, who's going to talk to us on a topic roughly about getting the measure of adult Aedes age, the important parameter in dengue epidemiology. So over to you, Professor Lyons. Thank you.
So thanks, Leo. Thanks, everybody. I feel a bit tentative here, speaking to so many people in such honorable company, because I'm a bit of a stranger in a strange land, and I don't mean in Southeast Asia, but in the world of Aedes and Aedes-borne viruses, because I'm really a mosquito, malaria mosquito expert. In the world of malaria, mosquito longevity is such a dominant part of the picture. And I look over the fence at the world of Aedes and dengue control, and I see less attention to that. So I asked why and started doing a bit of a reading, and just thought I would offer some quick thoughts. So in the world of that's what I'm going to be talking about, the why longevity matters in malaria, and a kind of demonstration, just some teaching slides to illustrate how that works visually for malaria, and I think probably also for dengue and other Aedes-borne viruses. A quick glance at how to measure longevity and the different ways it's done in the two different domains, and then also some other key features which make IRS and LLINs, adulticiding measures, the dominant form of malaria vector control, but not for Aedes, and that's really my primary question. In malaria, we can't forget that longevity matters, because, okay, you ask, why is most of the world's malaria in Africa? It's not primarily because Africa is the world's poorest continent, that health systems are relatively weak, etc., etc. Really, it's the fact that African malaria vectors are so efficient at transmitting the infection. And what makes them efficient? First, they bite man, but also they are very long-lived compared to others. Even within Southeast Asia, we ask, why is malaria in the region primarily associated with the forest? It's because the forest vectors are not only human biting, but long-lived. It's the longevity of those species, forest-associated species, that makes malaria essentially a forest-transmitted infection these days. Long ago, not like that. And then also, most importantly, what MacDonald pointed out in 1940 something, 50 something, why is IRS, and now we have LLINs them too, how come they can reduce transmission 50-fold even with 80% coverage? What makes that so powerful? It's about longevity. So just to explain the point, I invite you to imagine an Anopheles gambiae population in which 1,000 adults arrive every day. The daily survival rate's 0.85. It means 15% of every adult that's alive, all the adults that are alive, 15% of them drop dead every night. And the following day, therefore, of the 1,000 that we started with, 850 are left the next day. The day after that, another 15% drop dead, and we're left with 700 and something. We imagine that these feed on every 3 days, and with Anopheles, and God, we don't have the complication, there's relatively good gonotrophic concordance. In other words, 1 blood meal per gonotrophic cycle. Not like ADs. We assume that 20% of the blood meals are infective. In other words, a large proportion of the people have malaria, and that malaria is ready to transmit itself to mosquitoes that bite that person. And we assume that it takes 10 days for the parasite to develop inside the mosquito. So the mosquitoes that feed on day 3 here, those infections develop for 10 days, they come through on day 13, and of those still alive on day 13, which is a very small proportion of the 1,000 that we started with, less than 200 are still alive, but of those 20% become infected. On day 16, another cohort of infections come through, and the proportion infected jumps up until by day 19 and 22, the majority of the small number that are still alive, the majority of those are infective. They have sporozoites in their salivary glands. And so we look at the whole area here, which with those figures, recruitment of 1,000 per day, the total population is 6,500-ish. And the red area is 6.5%, about 6% of the total population is infectious. Now we imagine the same story, but now the daily mortality is doubled. Instead of 15% loss per day, we've got 30% dropping dead every day. So the survival rate 70%. We start off with 1,000, then it's 700, then it's 490, blah, 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 blah. And down here, you can see just that thickening of the line. Actually, that is the red area. And now the sporozoite rate, the proportion infectious, has dropped down to 0.4% of a population that's half as big. And so that's a very large reduction, nearly 50-fold reduction in the intensity of transmission just from doubling the daily mortality. So there's those two graphs redrawn side by side to show the same story. And there they are, exactly the same graphs, but now on a log scale to show what they look like that. Classic exponential decay stories. So is that what's going on in ADs? I was surprised to see not much attention to that comparatively compared to the malaria as well. How do we measure adult survival and longevity? Well, primarily by classifying insects according to their age. So here's the simplest way of doing that, de novo method, looking at the ovaries. We see nulliparous ovaries with these knots of tracheoles, which indicate she's never laid eggs. This ovary has never been stretched. And this one, which may be the same size, but has previously expanded greatly to fit the eggs, which were there and have now gone. And so those little knots of tracheoles were stretched out and they never spring back into that old knotted condition. And of course, there are complicated ways of age grading, the gold standard, very difficult to do, but an amazing amount of information if you can do it. This is looking at the ovaries at the ovariolar stalk. That's the ovariolar stalk through which the egg would normally pass. And these are the lumps left behind, the dilatations, as we call them, from previous oviposition cycles, when this follicle began to develop, but those follicles got reabsorbed. And so that count of how many lumps there are tells you how many times this female laid eggs. You can do that with Anopheles gambiae, and you can also do it with Aedes, although I don't think it's ever been done on a very large scale. This is the data we caught doing that, and it's really just to see, out of these 4,000-ish insects, here are the sporozoite positives, the ones that are 3 cycles or more older, 3 gonotrophic cycles older, so that's about 9 or 10 days older. And you can see that most of the sporozoite positive females are in these just old enough to transmit age groups. When you get to the very old ones, the ones who have been alive for ages, 3 weeks or so, the great proportion of them are sporozoite positive. So the proportion sporozoite positive transmitting, that's very high. But the bulk of the sporozoites come from the slightly younger age groups. The data, we were lucky to have this data from Tony Wilkes, one of the main, most skilled of these people who can do that fancy multiple age grading technique. He did it first, learning the technique from the Russians who brought it. In 1961-62, at the height of the Cold War, the group in Tanzania invited some Russian technicians to come and help, and that's the data that they got. And you can see that the slope of the line has slightly increased when the same dissector, Tony, was again there in 1987 with us. He did the same dissections again with the same mosquitoes 25 years later, and those were the results, implying a slight decrease in the probability of daily survival over that kind of period. What we did get from Tony's dissections during our little vector control, village scale vector control trial, one of the very first village scale deployments of ITNs. And we can see that in this one village, that was the slope of survival before intervention, and that was what it looked like after intervention. You can see down here this little kink. Those are tiny, tiny numbers of mosquitoes, so not to be worried about. It's that slope there we should be thinking of. And this, I think, is the best evidence anybody ever collected that MacDonald was right, that really it's not about reducing abundance, it's about reducing the survival of the mosquitoes and reducing the number that are in this dangerous age range. The same happened in the other village where we had treated nets. The numbers are not so good, not so high. And also in this village where we were spraying DDT. It's the same story. Now there's slightly more effect on overall abundance, but also an increase in the slope. So trying to measure this kind of thing, one has to remember that Anopheles mosquitoes fluctuate hugely in abundance. I don't know whether the same applies to Aedes. I suspect that it's relying on ovitraps isn't going to reveal this kind of huge fluctuation. And we really don't know to what degree this kind of variation, this is Derek Charlwood's data from a single light trap in a single house in the middle of a rice field in Kilimanjaro Valley, Tanzania. And you can see those fluctuations from day to day, very, very large. And probably these are fluctuations in catchability as well as abundance. We're not really sure. And then the other data confirming the age grading data, again from Derek Charlwood. Here he is recording the catches, those daily catches in decline from the moment here when he says it was clear that all recruitment had stopped. There was no new adults entering the population, and just recording now on a log scale the decline in abundance over about 2 logs, 2 orders of magnitude decline over the next month, and that corresponding to about 17% decline per day, daily survival about 83%. So very consistent with the other estimates, including those ones that we inferred from Tony Wilkes's data. So conclusion, yeah, between 15 and 20% mortality per day. I won't go into this, but just yes, one can use different methods to infer age. There's a lot of interest at the moment in near infrared spectroscopy and ways to improve that. From what I can see, that's very good, but there's a certain amount of inevitable noise in the data. So you're always going to need decent numbers of insects to get that right. You're not getting the individual insect precision that you do with the ovariolar dilatations. So what data is available from a quick perusal of the data for Aedes? There's a lot of information from just putting mosquitoes in cages and seeing how long they live for. And the answer is they live for a very long time, but that tells us very little, I think, about how they survive in the field. Clearly, the events that they do in the field, feeding, laying eggs, there are all kinds of predatory hazards there that are not there in the lab cage. There are decent numbers of papers reporting Paris rates, and looking at those again over the fence and having experience of looking at Anopheles Paris rates, these seem oddly variable. So there are papers reporting prolonged periods with less than 30% Paris rates, and others reporting more than 97% Paris over a very long period, over 2 months or more, which suggests extraordinarily long survival, low rates of mortality. And then mark recapture, not so many studies, only a relatively small number. And in these, interestingly, nice estimates of survival, but of course, with mark recapture estimates of survival, what you're measuring is loss, meaning the insects that are no longer there to be caught because they either died or they emigrated. Emigration is included inevitably. It's assumed negligible because in those studies often you get some measure of how much movement there is, and it's assumed that movement out of the study area is negligible. I wish I was more convinced. I can see that you can see in the data that the mosquitoes that you did recapture hadn't moved very far, but if you were doing the sampling further away, it's very difficult to sample over a wider radius. So that's my question. So just thinking, I wish we could see some more detailed age grading of Aedes, some time series analysis, which takes account of those fluctuations in numbers. And then the key point, what are the factors affecting longevity in the case of Aedes? And really the last thought, it's not just longevity. IRS and LLINs are core for malaria, partly because they both reduce longevity. And that's why we have, in the case of malaria, a vector control intervention that can easily reduce transmission by 50-fold. the epidemiological consequences of that are not a 50-fold reduction usually because of the effects of immunity in malaria. But transmission itself, the inoculation into people, that's reduced 50-fold. But also because these interventions are very robust. It means that because of that power, they are tolerant of less than perfect circumstances, less than perfect implementation, because of the residuality. And we saw the transformation from ITNs, which need to be retreated every year, to 3-year, well, not quite 3-year, but we pretend they're 3-year LLINs, which enabled us to go for universal coverage of those at risk in Africa, for 500 million people, universal coverage. And we're getting there. And then what enables that scaling up? It's the standardization. It's the fact that you need logisticians, not entomologists, to do effective LLINs in a very large community. And I think of trying to do community-based source reduction with ADs. And yes, of course, that's partly a logistic exercise, but also the relationship with the community, and then being precise about which containers you're worrying about. So yeah, just some thoughts. If I were working with ADs, I'd be thinking, how can we get that kind of intervention that has these characteristics? And what gives LLINs and IRS these characteristics? It's because the mosquitoes come to us. They come to the wall. Their behavior brings them to the LLINs. So what could we do with ADs that might have that characteristic?